Research Center. Schlumberger is a transnational oilfield services company. In particular, Schlumberger Moscow Research is a center of excellence in reservoir physics. So, today I want to present the results of work in painting of ring artifacts on microtomographic images by 3D convolutional neural network. So, let's start. Mathematical modeling of physical and chemical processes in the oil and gas industry is used to study the reservoir potential. For these purposes, digital rock is currently applied. In this case, the model is building based on a 3D image of a rock sample. One of the methods for obtaining the three-dimensional image is the X-ray microtomography. By micro-CT images contain various artifacts. Ring artifacts are very troublesome for digital rock, since those defects not only degrade visual quality, but might affect on subsequent image segmentation and flow simulation. Various approaches implemented in hardware and software of micro-CT systems allow suppressing the majority of artifacts. There are several algorithms for the reduction of ring artifacts on a reconstructed image. Nevertheless, part of ring artifacts remains. Since these artifacts look like scratches, we can apply inpainting techniques. Inpainting is a retouching technique that is very active over the recent 2 decades. Image inpainting methods can be divided into 2 categories: non-blind techniques and blind ones. In the first category, the regions that need to be restored are provided to the algorithm, whereas in the second, no information about the location of the corrupted areas is given, and the algorithm automatically identifies the regions for painting. Since we don't know regions with rings, we want a blind painting algorithm. We propose a workflow with correction and image using 3D end-to-end convolutional neural network for blind ring artifacts in painting. In contrast to other ring artifacts reduction algorithms, our algorithm can work with cropped parts of micro-CT images. Creation of big enough and the representative dataset is key for the success of techniques based on supervised learning. We need corresponding to each other pairs of fragments of images, undistorted and damaged by rings. For processing, we got 8 reconstructed 3D images of sandstones and sand in the presented size. Firstly, we segment artifacts on these images. In one of the previous works, we proposed the algorithm of ring artifact segmentation. It transforms image slices to polar coordinates, apply a matched filter, thresholding, and morphological operations for ring segmentation. Using this algorithm, we find all artifacts from all our images. Their total number was about 1500. Theoretically, we can reconstruct images from shadow projections with other parameters to obtain corresponding and distorted fragments. But this number of artifacts is not enough for the training of deep network. So, we propose ring artifacts transferring procedure. We take one found artifact and find differences between 10 averaged along columns rows and the median value of this averaged row. We translate each ring on multiple adjusted slices based on an estimated thickness distribution of real reads from the initial dataset. We randomly select 100 rings and place them in random positions in polar coordinates. With the presented workflow, we translate rings on the multiple slices. For validation, we use the UniFrag sand image, because it strongly differs from images of sandstones. To this image, we translate only 15% of found artifacts, And for training, we use the other 7 images and 85% of remaining artifacts. For training, we use Adam Optimizer. Every 100 iterations, we evaluate multi-scale structural similarity index of random 50 patches from validation image. And when the difference between previous and current evaluations becomes smaller than the presented value, we stop training. We use 3D unit with input with presented patch size, since only from 1 to 7 slices deteriorates by each artifact. The training of each tested model takes about 1 day. We test 3 loss functions: mean squared error, based on multi-scale structural similarity index, and weighted sum of multi-scale structural similarity index loss and mean absolute error. As for performance metrics, we use a multi-scale structural similarity index, mean absolute error for voxels without rings and with rings. The model trained with loss based on multi-scale structural similarity index shows the best performance and visual quality of Inpainting. Since we perform blind Inpainting, mean absolute error for voxels without rings is not 0. We also compare our best model with non-blind Inpainting algorithms. These algorithms also require mask of artifacts for Inpainting. The non-blind technique proposed by Ilia shows 0 mean absolute error for voxels without rings, since it changes voxels only inside the mask. The convolutional neural network proposed by Liu et al. Changes a small number of voxels around the mask. The ready-for-use convolutional neural network proposed by Liu shows bad performance, since it was trained on the ImageNet dataset that doesn't contain microcity images of rocks. With transferring learning, we retrain this model, and it gives better performance. But our blind solution is still better than it. As a conclusion, I can say that the trained network provides good numerical and visual results. Inference time is about 200 seconds for the entire microcity image. The proposed procedure of dataset creation can help to create a general solution across the microcity systems of any manufacturer. There is room for improvement. For example, the procedure of transfer of rings to undistorted slices can be done in true 3D manner. Thank you for your attention. I'll be happy answering your questions.